Okay, let's dive right into this explainer. Today, we're uncovering the hidden rules of spin. We'll be looking at the invisible math governing everything from a rolling wheel to a spinning gyroscope, focusing heavily on the mechanics of rolling, torque, and the ultimate law of rotation, angular momentum. Here is our flight plan for today. First, the anatomy of rolling. Second, the physics of the yo-yo. Third, torque as a vector. Fourth, understanding angular momentum. Fifth, conservation in the real world. And finally, we'll uncover the gyroscope's secret.
All right, Section 1, the anatomy of rolling.
Grounding this in reality, just picture a mail carrier cruising by on a Segway. Its smooth rolling motion is actually a perfect real-world laboratory for understanding center of mass translation and rotation. You know, when we see a wheel smoothly rolling across the pavement without slipping, our brains just naturally process it as one fluid action. But to effectively calculate the physics of a vehicle like this, we've got to look a bit deeper. Now, what's really interesting here is how we can split smooth rolling into two simultaneous actions happening at once: pure translation and pure rotation. Imagine you're moving alongside that Segway at the exact same speed it's traveling. From your perspective, the center of the wheel is stationary, and the outer edges are just spinning around it, right? Well, that's pure rotation. But if you completely lock the brakes so the wheel just slides forward, the whole thing moves as one solid block. That's pure translation. Rolling seamlessly combines these two states. And because of this mathematical combination, here's a wild fact. The very top of a rolling wheel is actually moving forward at twice the speed of the center, while the exact point touching the ground is for a split second completely stationary. No way, right? But it's true. So mathematically, this means a rolling object has to split its available energy into two separate buckets. One bucket is for moving its mass forward, and the other is for spinning its mass around an axis. It's mathematically represented as 1/2 I com omega squared plus 1/2 m v com squared. Because it basically has to pay this energy tax to rotate, a smoothly rolling ball will actually accelerate down a ramp a bit slower than a completely frictionless block that's simply sliding down. It is a perfect mechanical balancing act of energy. Moving right along to Section 2, Physics of the Yo-Yo. Stepping away from the street and into your pocket, let's explore the dynamic energy shifts within a classic toy. When you hold a yo-yo right before dropping it, it is absolutely packed with gravitational potential energy. As it descends, that energy is actively drained to fund those two separate bank accounts we just talked about: translational kinetic energy as it drops toward the floor, and rotational kinetic energy as it spins faster and faster. When it hits the very end of the string and starts sleeping, well, all the falling stops and it just sits there burning purely rotational kinetic energy. Now, to a physicist, a yo-yo isn't just a toy on a string. It is literally a wheel rolling down a perfectly vertical 90-degree inclined plane on a tiny central axle. Think about that for a second. The exact same equations of motion that dictate how a massive steel cylinder rolls down a warehouse ramp apply directly to the yo-yo unwinding down its string. The only real difference is that the ramp is replaced by the tension of the string, and the angle of the incline is pointing straight down. Let's head into Section 3, Torque as a Vector. Now, let's peel back the curtain on the abstract 3D math that makes all this spinning possible by examining torque. Torque isn't just a simple push, it's a precise 3D cross product of the moment arm and the applied force, calculated relative to a fixed origin point. Think about using a wrench to turn a really stubborn bolt. The position vector, r, is the distance from the bolt out to your hand on the handle. F is the force you apply. If you pull straight out, literally away from the bolt, the angle is 0, and you generate absolutely 0 torque. You only maximize the twisting action when you apply force at a perfectly perpendicular 90-degree angle to that moment arm. Grab your right hand and follow along with me here, because this physical right-hand rule perfectly predicts the exact perpendicular direction of any twisting force. Seriously, try it. Point the fingers of your right hand along the handle of our imaginary wrench. That's our position vector R. Now curl your fingers in the direction you're pulling. That's the force vector F. Now stick your thumb straight out. That outstretched thumb is the exact direction of the torque vector. It calculates that 3D alignment where vectors snap into perfect perpendicular alignment. Notice that the torque vector doesn't point in the direction you're pulling. It points straight up out of the wrench exactly along the axis of rotation. Kind of mind-blowing, right? All right, Section 4, Understanding Angular Momentum. Okay, let's build on torque to understand the ultimate rule of spin, angular momentum. Just as mass and velocity define straight-line momentum, angular momentum depends entirely on how mass is distributed around an axis and how fast it rotates. In linear physics, you know a massive truck moving fast is super hard to stop because it has high momentum. Well, in rotational physics, a heavy flywheel with its mass distributed far from the center, spinning rapidly, is incredibly hard to stop. We call this angular momentum, represented by L, and it equals rotational inertia I multiplied by angular speed omega. Check out this quote. This realization from Newton's second law in angular form is huge. It means that without an outside twisting force, the total amount of spin in an isolated system is locked in. It absolutely cannot change. Just like an object traveling through space will keep flying in a straight line forever unless bumped, a spinning object will keep spinning with the exact same angular momentum forever unless a net external torque acts upon it. Which brings us to Section 5, Conservation in the Real World. Let's see how this law of conservation radically affects human motion. Consider an Olympic diver or an ice skater. When they launch into a spin with their arms and legs extended, their mass is distributed far from their central axis. They have high rotational inertia, so they spin relatively slowly. But the moment they tuck their limbs tightly against their body, their rotational inertia just plummets. If an initially rigid body redistributes its mass closer to the rotation axis, its rotational inertia shrinks, which mechanically forces its angular speed to skyrocket. I want you to actively think about this for a second. If nothing pushes an ice skater or someone on a spinning stool to speed up, what invisible mathematical law are they exploiting to spin faster? Since there's no outside force twisting them, literally zero net external torque, their total angular momentum is completely conserved. It cannot drop. So, if the rotational inertia is suddenly cut in half by pulling their arms in, the angular speed must mathematically double to keep the equation balanced. They speed up simply by rearranging their own mass. It's a real game changer when you understand what's actually happening. And finally, Section 6, the gyroscope's secret. For our grand finale, let's tackle one of the most mind-bending anti-gravity illusions in all of physics, precession. If you've ever watched a spinning top seemingly defy gravity by rotating in a horizontal circle, you've witnessed this magic firsthand. If you place a stationary top on a table on its tip, it immediately falls over, right? Gravity pulls the center of mass down, creating a torque that tips it. But if you spin that top rapidly first, it doesn't fall. Instead, it leans slightly and starts sweeping its axis in a slow, continuous horizontal circle. So why doesn't it fall? The crucial point is that gravity's downward torque interacts with the gyroscope's pre-existing angular momentum, forcing the spin vector to chase itself in a circle. Remember that cross-product math we did with the wrench? The torque created by gravity points horizontally. This horizontal torque acts upon the existing angular momentum vector of the spinning top. Because they're perpendicular, the torque doesn't change how fast the top spins. It only continuously changes the direction of the spin. The top's axis is forced to constantly rotate its orientation, creating that mesmerizing continuous horizontal sweeping motion. And as we wrap up this explainer, I want to leave you with this massive final thought. If conservation of angular momentum governs a pocket yo-yo and a tiny gyroscope, what invisible forces are keeping the Earth itself steadily precessing on its tilted axis right now? How does the very planet you're sitting on obey these exact same hidden rules of spin? You see, the Earth isn't just moving through space. It is an enormous, spinning gyroscope, tilted on its axis, bulging at the equator, and constantly experiencing torques from the gravitational pull of the sun and the moon. This cosmic interaction causes the Earth's axis to precess in a massive circle over tens of thousands of years. From a tiny plastic yo-yo to the planet beneath our feet, it is all the exact same beautiful, hidden physics. Thanks for diving in with me.